Hello everyone, I hope you're doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is good subtrees and it is a medium level problem. So the problem is very straightforward and you can see by the accuracy like it's 90% that this problem is not very difficult and it's a very standard problem. So before starting today's problem, I wanted to discuss something. Yesterday, I posted a poll whether anyone was interested in a video on lambda functions in C++ or not, and I got an unexpectedly good response. So I decided that I'll be making a video on the lambda functions. So I'll post this video on like by Sunday or Monday. So I'll keep you guys posted about it, but I'll try my best to post it before Monday. So that's it, and let us quickly start with today's problem of the day. And this problem says that we have been given the root of a binary tree, and like each node has been assigned some value, and we have been also given an integer k. Now we have to count the number of good subtrees. They have defined a good subtree, which is a subtree such that the number of distinct values in its subtree is less than or equals to k. Right. So let us just discuss the first sample test case that has been given to us. So they say that if this is a tree, right? So the first node at the top is 1. First node at the top is 1. The second node here is 2. Third node here is 3. Then again its value is 2. This is 5 and this is 4. So what do we mean by subtree? Subtree starting from 2 is a tree like this. This particular for this particular 2, the subtree is this. For this particular 2, the subtree will be this. So all the nodes which are its children or the children of its children can go on. So if this is like this will also be a subtree of 2, right? So this is what we call subtree. Now what happens? We are asked to find out how many subtrees are there such that the number of distinct values in that particular subtree is less than or equals to k, right? So if we talk about this particular subtree, there is 2 and there is 3. So the number of distinct values is 2, right? So this is one possible answer. Let me just write it here. This is with this particular arrow I am indicating that this is a good subtree. Now again, since there is only one value here, this is a good subtree. There is only one value here, this is a good subtree. This is a good subtree, definitely, right? Because in all of these nodes there are only one value and they have no children. So if like 5 had some other children as well, like 6 or 7, then this particular 5 would not have been a good subtree. So in this in the current scenario, it is a good subtree, and you see there are only 4 arrows that I have marked, so there are 4 good subtrees. If you try to consider this particular 2, you will see that the number of unique elements are 2, 4 and 5. So there are 3 unique elements, so this cannot be a good subtree since the value of k is 2. Now for this particular root node, the elements in its subtree are 1, 2, 3, 4 and 5. So there are 5 unique elements and hence it cannot be a good subtree. So this is the problem explanation. Now how do we solve? When I said it is a standard problem, what did I mean by standard problem? So whenever we want to do something with a subtree or we want to process some queries, there is a very general way of solving this problem, and I'll share you how we can solve this particular problem. So it says that for example, if we have been given a node and its answer depends on the subtree or on its children basically, right? So we are talking about subtrees, so the answer for each node will depend on its children, right? So how do we answer these queries? So first of all, what we'll do is every node passes some value to its parent, right? And what will be this particular value? Let me just write it. Every node calculates its own value from its children, right? So these are the two things that we generally have to do in these kind of questions. So every node will pass some value to its parent, and what will be this particular value? This particular value will be calculated by the node. It calculates its own value from its children, right? So every node will receive some data from its children. It will do some processing on it and pass the next data to its parent, right? So this cycle goes on. Now, how do we solve this particular problem with these 2 points in mind? So, in the constraint, it was mentioned that the number of unique nodes or the data in the node can be only up to 25. So, it is in the range 1 to 25. 1 to 25. Right. So, there are multiple ways of solving this problem. What I tried was, for each of the nodes, I was trying to maintain a vector. Right. This will be a Boolean vector, and for each position, it will show whether the current element is present or not. Right. So this is what I was doing. So if the Boolean vector looks something like this for any particular node, it will denote that 2 and 5 are present, right, in that particular subtree. So for example, if I want to construct this particular vector for the node 2, I'll construct it like this. So if this is 1, this is 2, this is 3, this will be 0, this will be 1, and this will be 1, right? So you see that for every node I'll maintain this type of Boolean vector, and since the number of unique values are only up to 25, maintaining this vector is not very difficult as well, right? So what I'll do is I'll just check how many ones are present in this particular vector. Since the number of ones is less than equals to k, that means it is a good subtree. Now I don't know why, but this approach was giving TLE. So like what I believe what should have happened is, the number of nodes are n. Since we are doing a simple traversal, the overall complexity of traversing the node should be O of n. The tree should be O of n only. And if you multiply it by each vector, so for example, in each time or for each node, we'll have to traverse this particular vector once, right? So for that, the complexity should be at most 25, right? So the overall complexity is 10 to the power 5 into 25. So it is 2.5 into 10 to the power 6, I believe. Right. I believe like this should have worked, but due to some reason it did not. So what I did was, like, I was maintaining my overall approach was same, but that way I was checking how many unique elements are present in the current node. I changed I did it using a set. So for a set, what I have to do is, since the number of unique elements in the set would be at most 25, so it would be n into log of 25, right? Earlier what I was doing was, like, I was traversing the whole array in n time, or where n is the size of the array. In this particular case, where n is 25, let me take it to be m, right? So earlier I was traversing the whole array of size m is equal to 25. Now I'm using a set, and since the number of operations in set is log m, right, the maximum size of the set we know is 25. So like the rough complexity would be n log 25. So this factor reduced from constant 25 to log 25, and this approach worked. I don't know, like I believe that this approach should have also worked, but time constraints on Geeks for Geeks are very strict, so it did not. If you, I'm sure, like if you try it on some other platform like Code Forces, since this is very less, it is around 10 per 6, it would work. So till now we have discussed what kind of data structure we will use to maintain the number of unique elements in a subtree of any node, right? So instead of using a Boolean vector, we will be using a set. So what are we actually going to do in the code? So for example, if I am at any node, I'll just create a set, right? I'll insert the current value. So this will be node data, right? So I'll just insert the data of the current node. Now I'll just call a simple DFS on the left hand side and a simple DFS on the right hand side. Both of these nodes, its children, will return some value, right? They are also going to return a set. So let's say this is set 1 and let's say this is set 2. So I am going to insert all the values of set 1 and all the values of set 2 in my original set, right? So what are actually set 1 and set 2? Set 1 are the number of unique elements in the subtree of this particular node, in the left node, and the set 2 are the number of unique elements in the subtree of the right node, right? So when I get all of this information in the current element, right, in the current node, what I'll do is I'm just writing it like this: set 1 plus set 2 plus node data. If I do this particular operation, this plus operator means I'm going to combine all of those values. If I do this operation, in the current set, I'll have all the values or all the unique values in the subtree of the current node, right? So I'm just going to insert all the current node data in a new set and all the values from S1 and all the values of S2. If the size of the final set is less than equals to k, that means the current subtree is a good subtree. Otherwise, it is not a good subtree. Again, this might be a child of some other node, so this is going to pass its own set to this particular node, right? And this process will keep on repeating. And what happens if you are at a null node or null pointer? The null pointer will return an empty set to this particular node, right? This is what is going on in this particular question, and this is how we are going to approach this particular problem. So you see, we have like taken care of these two points in mind, that every node calculates its value from its children, right? So the left node is returning S1 and right node is returning S2. So these two nodes and the value of the current node combined creates the number of unique elements in the subtree of the current node. Now this particular node is going to return this particular set to its parent. So every node passes some value to its parent, right? So from here it is going to the parent. This is what will be happening. So let me just quickly summarize what I just said. So like every question you find of this particular type is going to have a similar pattern of solving, and you have to keep in mind these 2 points that I have just explained, right? That every node passes some value to its parent and every node calculates its own value after receiving some value from its children, right? So this is what will be happening. Now we needed some kind of data structure to store the number of unique nodes in the current subtree, right? Or store the number of unique elements in the current subtree. So since the number of values that have been given to us in the question are only up to 25, this was the constraint mentioned in the question, I decided to use a boolean vector denoting what are the values present in the subtree of the current node. But due to some reason on Geeks for Geeks, this particular approach was not working and I was giving clearly. According to me, the overall complexity would have been 10 to the power 5 into 25, where 25 are the number of unique elements. But this did not work, and hence I used a set to store the number of unique elements in any subtree. Now, once I've got the number of once I've got a way to store the number of unique elements in any subtree, now I have to apply these 2 points that I've discussed before. So what I do is, I just, for every node, I just insert the current data into the set of the current node, right? So the current data is the element present at the current node. Now I will be receiving some values or a set from the left subtree, and I will be also receiving a set from the right subtree. I combine the values from all those sets and the current node and check whether the size of the new set is less than or equals to k or not. If it is less than or equals to k, I will increment my answer by 1 and then pass the current set to its parent, right? This is what will be going on, and let me just show you the code now. So this is my code. I have initialized my answer with 0. This is my simple DFS function, and I've called this DFS function here. So I have called it on the root. Now what will happen is, I created a set called current. So this will be the number of unique elements in the current subtree. Now if the node is equals to null pointer, I'll just directly return current, because current is an empty set. Now otherwise, if it is not a null pointer, I'll insert the current element into the current set. So this is node data, right? Now I'll receive some set from the left DFS, I'll receive the set from the right DFS, and for all the elements in the left, I'll just insert it into the current set. For all the elements in the right, I'll just insert it into the current set, and I'll increment my answer if current dot size is less than or equals to k, right? So this will increment my answer by 1 if current dot size is less than or equals to k. Now I'll just return current to its parent. So this is what will be going on. At the end, I can just return my answer value. So this would be the solution of today's problem of the day, good subtrees. I've tried to explain you in a way so that if you get any problem of the similar kind, you'll be able to solve it. So that's it for today's video. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video. So I see a lot of people who watch these videos have not subscribed yet. So if you're one of them, please consider subscribing to this channel. It's always free of cost, and you can always unsubscribe later if you don't find the videos interesting. And till the next video drops, keep coding, stay safe, bye bye.